Good afternoon. I am Dr. Pratyay Konar. Today I will start with the topic of single phase transformer. First of all, we need to know why we are going to go through single phase transformer. Transformers are the heart of electricity supply industry. The power transmission system using transformer is shown in the figure. You can see here that from a generating station, with the help of transformer, we have stepped up the voltage from 33 to 13.5 kV, and thereafter another transformer from 13.5 to 6.6 kV. That is, we are transmitting voltage at a very high level to the distribution station. From distribution station, we are supplying the power to the consumer as well as to the industry. So that's why there are two types of transformer. For the consumer, the voltage is stepped down at 440 or to 240, and for the industry, generally up to 415 kV volt. Now, when the transformer changes voltage level, as you can see, the transformer is changing the voltage level. It also changes the current level also. Introduction to the transformer. What is transformer? Transformer is a static device which is used to transfer electrical energy from one AC circuit to another, interlinked by a common magnetic circuit. We will come to this figure later on. Without any change of frequency. This is very important. Input to a transformer and output from a transformer are both alternating. That is, there is no change of type, that is from AC to AC. Electrical energy is generated and transmitted at an extremely high voltage, as we have seen in the previous diagram, and can be reduced to a lower volt value for its domestic and industrial use by using a transformer. Now, construction of transformer. As you can see, here we have laminated core, and on either side there is two windings. This is called the primary winding. This is called the secondary winding. An elementary transformer consists of soft iron or silicon steel core and two windings placed on it. As you can see from the figure, the windings are insulated from both the core and each other by thin insulation materials. The core is built up of thin soft iron. As you can see, there is a lot of laminations over there to reduce the eddy current loss, and these thin sheets are separated by varnish. The windings connected to the supply main is called the primary winding, as I have already told, and the winding connected to the circuit is called the secondary winding. Basic principle of operation of transformer, that how the transformer is transferring energy from the primary circuit to the secondary circuit. As you can see, this is the core material shown, very simplified diagram where the laminations are not shown, and as we have previously discussed, that this is the primary winding, this is the secondary winding, and you can see we are supplying the primary winding. The primary winding is connected to the single phase AC supply, and AC current starts to flow from the primary winding. And you can see as the current starts to flow, a magnetic flux phi denoted by the green line starts to operate in the core. So in the same core, the secondary windings are also wound. So this winding will also be linked with the flux, and the primary winding will also be linked with the flux. The primary AC current produces an alternating flux phi in the core. Most of this changing flux gets linked with the secondary winding through the core, as I already said. The varying flux will induce voltage into the secondary winding according to Faraday's law of electromagnetic induction. The voltage level changes, but frequency remains same. There is no electrical contact between the two windings. Electrical energy gets transferred from one circuit to another, that is the primary to the secondary circuit, by electromagnetic induction. As in the point mentioned over here, voltage level changes but frequency remains same. Why? Because both the primary winding and secondary winding are linked with the same flux, and there is no rotating part associated with the transformer. So the frequency remains same. The induced EMF in the secondary winding enables it to deliver current to the external load connected across it. Because as you can see that in the secondary winding, if a load is connected, the circuit is completed, so its current will flow. The induced EMF in the secondary winding enables it to deliver current to an external load connected across it. Thus, the energy is transferred from primary winding to secondary winding by means of electromagnetic induction without any change of frequency. I am all the time I am telling that there is no change of frequency. It's very important point to note. The flux phi of the iron core links not only with the secondary winding but also with the primary winding. So produces self-induced EMF in the primary winding denoted by E1, and in the secondary winding, this induced secondary winding, the voltage is induced by mutual induction. This induced voltage in the primary winding opposes the applied voltage. In this way, the induced EMF in the primary winding limits the primary current, which we will go in detail later on. What is an ideal transformer? An ideal transformer is an imaginary transformer which has the following properties. Its primary and secondary winding resistances are negligible. As you can understand, the primary winding and secondary winding wires are wound on the limbs of the core. So each wire should have some resistance. Even if the material is used of copper having a minimum resistance, but still there is some amount of resistance in the winding. In ideal transformer, we are neglecting that resistance. So primary and secondary winding resistance are negligible. The core has infinite permeability mu, so that negligible MMF is required to establish flux in the core. Its leakage flux and leakage inductance are zero. The entire flux is confined to the core and links both the windings 100%. There is no losses due to resistance, hysteresis, and eddy currents. Thus, the efficiency is 100%. Practical or commercial transformer has none of these properties in spite of the fact that its operation is close to that of the ideal transformer, because we have only neglected the resistances which are very negligible, and as well as the permeability of the material is almost infinite because cold roll grain oriented material is used to construct the core, as well as laminated sheets are used to reduce the eddy current loss, and the core material is made of steel to reduce the hysteresis loss. So understand that the losses are very negligible. So performance of the practical transformer is somewhat similar to the ideal transformer, but for simplicity, we will deal with the ideal transformer, then we will move to the practical transformer. Now, very important question, that can the transformer operate on DC? You recall that we have said that the operating principle of transformer is Faraday's law of electromagnetic induction, and by Faraday's law of electromagnetic induction, the energy is transferred from the primary to the secondary. So, will it operate in DC? No, definitely not, because as per Faraday's law, there will be no change of flux, and so no induced EMF in the primary and secondary. So, no power transfer will take place from the primary to the secondary. The transformer action does not take place with direct current of constant magnitude, because with the direct primary current, that is, if the primary is supplied with DC, the flux produced in the core is not alternating but it is of constant value, because Faraday's law is not taking place. As there is no change in the flux linkage with the secondary winding, the induced EMF in the secondary is zero. Moreover, if DC is applied to the primary, then there is a possibility of transformer core saturation, because the current is constant. If core saturation, the primary will draw excessively high current. Therefore, application of DC should be avoided, and this is very important. Now, transformer types. The transformers of a different type depending on the arrangement of the core and the winding as follows: core type and shell type. The magnetic core is a stack of thin silicon steel laminations about 0.35 millimeter thick or 50 Hz transformer. In order to reduce the eddy current losses, these laminations are insulated from one another by a thin layer of varnish, as I have already mentioned in my previous slides. Types of transformer based on voltage: step-up transformer and step-down transformer. Based on construction, as already mentioned, Konar transformer, shell-type transformer. Based on applications: instrument transformer, auto transformer, leakage transformer, and resonant transformer. And based on supply, single-phase transformer and three-phase transformer. And very well understand that we are dealing with single-phase transformer, that means supply will be single-phase. The transformer, as I already have discussed in my previous slides, that from the generating station, two transformers are used to step up the voltage to supply the power to the distribution stations, and from distribution stations, the voltage is again stepped down to be supplied to the consumer and within industry. That means these two transformers are step up transformer and these two are the step down transformer. Now, what is core type transformer? Why it is called core type? As you can understand that there are the two limbs of this transformer, and you can see that two windings are placed on either limbs. This is the primary winding, this is the secondary winding, and you can see that how it's constructed. This is shell type. Why it is shell type? Because you can see here there are three limbs, and in the middle limb the windings are wound. First the low voltage winding is wound, and on top of that the high voltage winding is wound. Now, what is the difference between the core type and shell type transformer? The core type has only one window. As you can see, there is one window. One window is there because it's a square shaped core. And in case of shell type, there are two windows. Two windows is there. So the first point said that the core has only one window, and in shell type the core has two windows. Winding encircles the core encircles the windings. You can see the refer to the figures. The core is covered by the windings, that is windings takes most of the place, and in shell type the winding, it seems that the winding is covered by the shell or the core. Point number 3, cylindrical windings are used in core type transformer, and in shell type it is not easy. Sandwich type of windings are used. In core type transformers are easy to repair, shell type is not so easy to repair. Core type better cooling since more surface is exposed to the atmosphere, and shell type cooling is not very effective. Now, EMF equation of transformer. Before we derive the EMF equation of transformer, let us assume that N1 is the number of turns in primary, N2 is the number of turns in secondary, phi m maximum flux in core in Weber, that is Bm into A, where Bm is the maximum flux density and A is the cross sectional area. F is the frequency of AC input in Hertz. Flux increases from 0 value to maximum value phi m in 1/4 of cycle. If you consider the sinusoidal waveform of flux, that means to reach the maximum flux phi m, it takes 1/4 of the cycle. That means the time to reach phi m flux is equal to 1/4 by t, where t is the time period. Or else we can write phi m is equal to 1 by 4 t means 1 by 4m, because time period t is equal to 1 by f. So average value of change of flux d phi by dt is equal to phi by 1 by 4f. Or else we can write 4f phi m Weber per second or volt. Because rate of change of flux means voltage in term, as per Faraday's law of electromagnetic induction, EMF is equal to d phi by dt. So the unit is volt. Now rate of change of flux per turn means EMF in volts. That is E is equal to N d phi by dt. average EMF per turn will be 4F 5M volt. If flux phi varies sinusoidally, then RMS value of induced EMF is obtained by multiplying the average value with the form factor 1.11. The form factor is equal to RMS value by average value is equal to 1.11. RMS value of EMF per turn is equal to 1.11 is equal to 4F 5M, and we have derived in the previous slide. So it comes out to be 4.44 F 5M volt. Now RMS value of the induced EMF in the whole of the primary winding having N1 number of primary turns, induced EMF per turn into number of primary turns. That is E1 is given by 4.44 F N1 5M, that is equal to 4.44 F N1 BMA. It's question number 1 for E1, where A is the area of the core. Similarly, RMS value of the EMF induced in secondary is given by EMF per turn into N2. That is E2 is equal to 4.44 F into 5M is equal to 4.44 F into BM into A. Thank you. This is up to this single phase transformer. In next class, we will go for the other topics. Thank you.